Hi everybody! Today we are going to talk about textures in Vulkan. This video was created by Lukas 1214 and I'm JC, aka beaumanvienna, and I'm doing the voiceover. This video is based on the YouTube series from Brandon Galea about a Vulkan-based game engine after episode 28. Okay, what do we need to do to render a texture? In a nutshell, we will load the texture on the CPU side. We will copy the texture data from the CPU into a host visible staging buffer on the GPU. We will create an image object on the GPU. We have to transition the image layout to be ready for texture upload. We copy the data from the staging buffer memory into the image object. We transition the image layout to be shader readable. And lastly, we have to add a sampler for the texture to the descriptor set of our pipeline. For loading images, we're going to use the free and open source library stb. We need to copy its header file stb_image.h to the external folder in our project. We're then going to create two files in the source folder, texture.cpp and texture.hpp. In texture.h, the constructor of the texture class is going to take an LVE device and a file path of a texture. We will delete the copy constructors because the class is using memory pointers internally, so there should only be one texture object on the CPU representing a texture on the GPU. The texture class is going to have a reference to an LVE device, a VK image, VK device memory, a VK image view, and a VK sampler. Our texture class will also store the image format and the image layout. We need a private function to help transition the image layout. Now on to texture.cpp. Before we do anything, we will create a destructor to destroy all Vulkan resources so we don't get errors from the validation layers when we shut the app down. With stb_load, we will load the texture. Now we need a buffer to upload the data into that is accessible on both the CPU and GPU, which we call a staging buffer. The staging buffer is going to have the bit transfer source enabled. The memory properties have the bits host visible and host coherent enabled. There's already a handy function in our engine to write data to a buffer. Now we will create a 2D image with the format RGBA8_sRGB. Its initial layout will be undefined. The image extent, aka the image dimensions, correspond to the width and height that we got from the stb_load function. There's already a feature in our engine for creating images. Then we need to transition the image layout to be able to load the texture data from the staging buffer into the image object in the core of the GPU. After the data is loaded into the image, we transition the image layout again so that shaders are able to read the image. For reading texels from images, we need a sampler that dictates how the image should be read. The filters of the sampler will be set to nearest so that the image isn't blurred. We're going to set the address mode to repeat. Then we must not forget to create an image view, because in Vulkan, images aren't accessed directly. Image views provide metadata for an image. Next, we need to code a function to transition the image layout. First, we need to get a single-time command buffer to execute a pipeline barrier. For the image memory barrier, we will set an old and a new layout, which we get from the function parameters. Now we add some logic to handle access masks and stages. After executing the pipeline barrier, we need to end the command buffer. Now onto our game application, firstapp.cpp. We include the texture header, then we create a texture. We need to add to our global descriptor layout a new binding with the type combined image sampler. Don't forget to add the same type to the descriptor pool. To write an image to a descriptor set, we need to pass a struct with information about our texture. For the shader, we need fragment UV coordinates. We also need to add a binding for our texture. The layout will be in set0 binding 1. It will have a type of uniform sampler 2D and it's called image. With the texture function from GLSL, we will read each pixel into our image variable. In out color, we will change frag color to the image color variable. Now we can build our project. We should see all the game objects having our texture on them. There's one more thing we need to implement, mipmapping. As we can see in this picture, there's some strange warping. There are two methods to generate mipmaps. The first method is to blit images. The second method is to use a compute shader. We're going to use the first method as it's easier to implement. In texture.hpp, we add a private function to create mipmaps and variables called width, height, and mip levels. In texture.cpp, we delete the variables width and height because we declared them in the header file already. Then we need to calculate the number of mipmaps. We're going to use this equation for it. Now we changed some variables. We need to add the transfer source bit in image info.miplevels for mip levels and for usage. We need to delete the transition function and replace it with a new function to generate mipmaps. In image view info, we need to change the level count from 1 to mipmaps. Finally, we can go to the code of the function generate mipmaps. First, we need to check if the image format supports splitting. The function requires a VK physical device, but we don't have a getter function for it. So in lve_device.hpp, we add a getter. We also need a single-time command buffer and a pipeline memory barrier. We declare variables with the dimensions of our texture. In a for loop, we go over all mipmaps. This code here transitions the image to be ready to read. It copies the image and transitions the image back. After the for loop, it will transition the image layout again. After all of that, we will end the single-time command buffer. And that should be everything. Please leave a like on this video and subscribe, and good luck with Vulkan textures.